In question number 4, you're asked to sketch this graph showing the intercepts, the turning points, and justify the nature of the turning points. Now, aquatic is probably beyond the course, so this is a problem where you should use your graphics calculator to assist you. Now, you can see when you put that function in very quickly, if I go analysis, I've got my minimum at positive a half, negative 1.688, and that would be negative 27 over 16. And I'm going to have a point of inflection. Now you can probably see that's at negative 1, 0. But I'll just check that using the calculator. You can see inflection there. Yep, certainly enough, negative 1, 0. So it means I'll have a 0, a triple there if you like, at negative 1, 0. You can see I've got a 1, 0, 0 and a triple at negative 1, 0. So it would be very important to have that background information in order to do this problem. Beyond the course, but worth a while looking at. Now, first thing I do, as we've done for a long while now, the y-intercept, when x is 0, negative 1. Now, the x-intercept occurs when y is equal to 0. And look, I have to do some fiddling around here. If I plug in, and I know that from here, f is equal to 1, 0, so x minus 1, a factor. So I'm solving for when y is equal to 0, and I'll end up with x cubed, 3x squared plus 3x plus 1. And I'm hoping you can identify that that's x plus 1 triple is equal to 0 to the power of 3. So therefore I'm going to have zeros at x is equal to 1 and x is equal to minus 3, a triple, that point of inflection. So I'm a fair way into the problem now. Now for the stationary points. For the stationary points, I've got to take the derivative and solve for when dy over dx is equal to 0. And when I work that one through, and yes, I know x plus 1 is going to be 1. So I'll take x plus 1 out. And very quickly you should see 2x plus 1 all squared. 2x minus 1 is equal to 0. So therefore x is equal to negative 1 and x is equal to a half. And when I substitute that in, that will give me the point negative 1, 0. And I'll leave you to do the other one and just quickly give you a half, negative 27 over 16. Now in a moment I'll sketch that graph and I'll show you how to justify the fact that we have a point of inflection as well as a minimum. Now to put all those facts together, I've got a point of inflection, I've got a y-intercept, I have a turning point at a half, negative 27 over 16. I can put all those things together. So I show a point of inflection curving like so, bottoming out there and rising through there. Now what remains is for me to justify the nature of the turning points. And that's looking at the sign of the derivative. Now the approach I tend to take is to have a look at a few things we know about. We know at negative 1 dy over dx is going to be 0, and we know at a half it's going to be 0 as well. I'm just going to choose some relatively arbitrary numbers around those points to check out what could occur. -2, 0, and 1. The remainder, dy over dx, is equal to 4x cubed plus 6x squared minus 2. Now, when I plug that in, that's going to be -2. And when I plug 1 in, that will be 4 and 6 and minus 2, which is 8. So already I can see the sign goes from minus to 0 to positive, which is typical of the pattern of the minimum. So I can write that one down. And when I plug in -2, that'll be, well, the negative's just going to take over there. It'll end up being -10. So what I've got here, I've got a negative to 0 to negative. So as a round, x is equal to -1, negative to 0 to negative over point of inflection. So even though that is slightly beyond the course, for a bit of patience and obviously using your calculator to help, you can work that out.